Alright, so I'm going to do a little introduction here to contactors, which is basically a step up from the relays that were done in first year. I say a step up because what a contactor actually is a heavy duty relay. It's really all it boils down to. Um, Whereas relays are usually a throwaway device. If they fail, often contactors have changeable contacts, um, changeable coils, so that we can adjust them for our coil is changeable, so we can adjust them for different voltages and whatnot. Um, and they're physically bigger and able to withstand a lot more current, right? Your typical relays, up to 15 or 20 amps. Contactors can be rated for up to thousands of amps of current. Okay? All contactors, like a relay, some focus here. Focus needs more focus. It's not going to work very good. Although you can't really make it out in this recording, your contactors will all have a voltage and current voltage rating for the operating coil, which is your magnetic solenoid that's going to pull your armature to change your contact position, and it's also going to have a contact current rating and voltage rating. And a contactor may also have a horsepower rating, which means that it's suitable for use to start and stop an electric motor. Okay. This particular contactor right here is a Form C contactor, and what that means is that the contacts contain both a normally closed as well as a normally open set of contacts. So when this contactor is first is connected, we're going to have continuity from this contact to this contact, right up through this wire. And then when we energize the coil on the relay or on the contactor, the armature will move, and that will give us continuity between this contact and this contact. So schematically, the way these are drawn is our power contacts. Basically, we have a normally open as well as a normally closed set of contacts, and we can have those run to a variety of loads. Maybe we'll want a light to show up. Maybe we're going to have a green light to show that one status of the situation, whatever this thing's operating, and perhaps a red light to show the other operation of the circuit. And we're going to have a power circuit that looks something like this. Okay? So, well, why would we do that? Well, we could have a power circuit, something like this. Maybe we'll have a situation like this where we've got a switch that's going to turn a heater on and off, right? So we could use contactor 1 to show us, well, the light's going to be green when the heater's off. We energize this circuit. These contacts will change position. That'll mean this contact will turn, or this light will come, this red light will come on, the green one will go off, and at the same time that heater is going to come on. So we're going to have a red light to indicate every time this heater is energized. Could be, right? Now, why do we use contactors and starters? Well, there's a few different reasons. Number one, this could be 24 volts. What if we have multiple voltages that we want to use? Maybe because of the location of that switch, we don't want to use any more than 24 volts for our control voltage. That used to be done quite a bit. If you've got areas where it's, there's quite a bit of moisture, any intrinsically safe devices, so stuff that's going to be in an explosive atmosphere, but we want to make sure that we can keep cool and reduce sparks. We're going to deal with that, what that means in third year. There's various reasons you might want a really low control voltage. Our lights, well, we want to use 120 volt lights, but that heater, maybe it's a 600 volt heater, right? So by using a contactor, we can use a 24 volt supply to switch multiple voltages, okay? The other thing is, this heater could be a 10,000 watt heater. At 600 volts, it's going to have quite a bit of current flow, right? 10,000 watt heater at 600 volts. Okay, Kelvin. This heater, 10,000 watt heater, is going to draw 16.67 amps. This switch only has to carry the amount of current that it's going to take to operate those coils, which is going to be usually less than 0.5 amps. And then of course those little LEDs, they'd be the same. Very little current draw there. So we can have so that allows us for our switch to operate, in this case, at low voltage and at low current, low energy. With the switch, we don't have to make and break that 17 amps of current flow that's going to happen all the time. Again, lots of reasons for that. What if the distance between here and here, what if that's 500 feet, right? Maybe this switch is located in a remote area, and it's going to control a heater, in another building or whatever the case may be. Well, the conductors that are going to go out here and carry this half an amp at 24 volts, not going to have to be all that big, right? Probably a set of 14 gauge wire, a pair of 14 gauge wires will do that just fine. We try to run that distance to a switch that's carrying 20 amps. Well, with your voltage drop and everything, you're probably going to be around the number 6s or bigger, just to compensate for the voltage drop. So obviously there's quite a bit of savings there, right? 500 feet's maybe a bit of an exaggeration, but even if it's 100 feet, which is not unheard of in a big shop or whatnot. So that's kind of the reason that we use contactors, and where they fit into our world.